All right. Thank you for the introduction, and I'm very grateful to the organizers for inviting me to participate in this session. While I'm not going to be speaking specifically about agricultural sensors, I think that it was nice to have the broader perspective provided in the first talk, and hopefully some of the advancements that I am able to show you you'll understand the relevance to the broad need in the sensing community and new ways of approaching fabricating relevant devices. So to start things off, there we go. I just want to make a quick plug in general for those who study any type of transistors, whether they're high performance transistors or thin film transistors for sensing devices. We did have this article come out from a very diverse collection of researchers in industry, academia, and whatnot regarding how best to go about benchmarking these devices. Since this tends to be a community that brings together a variety of disciplines, I think it's important that we have some foundation we work from with respect to how we report the performance of different devices that we study. And so this paper provides a recommendation on that front that I encourage you to consider. So this is just an overview of the things I'll talk about, and mostly making a case for the use of nanomaterials and the benefits they provide in enabling diverse types of electronics, and then the potential to fill a need for more sustainable electronics by using nanomaterial-based inks for printing these devices. So at a bit of a high level around this point of sustainability, I do want to point out that in the US and around the world, there's this growing excitement around semiconductors. And the excitement obviously was driven by a pain point. That is often the case. The pain point is the supply shortage that we experienced over the last few years in the industry. But it has a positive outcome, the outcome being an increased drive to invest into new research in the area. The question that I had come up though now is, even though we have excitement in the US, we have things like the CHIPS and Science Act, I'm really becoming curious about whether we care enough about the environmental impact of newly developing technologies to prioritize that aspect of manufacturing. So in other words, if you think about what the future holds for a sustainable electronics community, it's not enough just to add better water treatment facilities or more renewable energy sources on large fabs. There has to be some more transformative path towards getting to a sustainable electronics future. So that's part of a motivation for some of the things that I'll show you today. So first of all, nanomaterials, in case there are any present who don't work with nanomaterials of any type, nanomaterials come in a variety of dimensionalities, constrained to 1 dimension, 2 dimensions, and larger. And they tend to share a few positive attributes in common when it comes to using them for electronics. One of those attributes is their ability to be processed in solution phase, so that they are compatible with generating a variety of inks that can be used in printing techniques. And one of the nanomaterials I've spent most of my career working with is carbon nanotubes. Again, one that most in the community have at least heard of, if not worked with. In this recent review article that I wrote with Mark Hurst and Philip Wong, we talked about the development of carbon nanotube-based transistors, and that includes transistors that are applicable to sensing devices such as flexible, biodegradable platforms, as well as those that would be in high-performance transistors like on the CPUs for your smartphones. And so in walking through that, it was a really good way of remembering how the nanotube-based devices have evolved over the years, starting with single nanotube transistors all the way to where we now see thin film devices being used in these more tangled arrays that you see down in the bottom picture. And one of the things that I want to make sure is clear when talking about the use of nanotubes in printed devices, and this goes for things well beyond nanotubes, is why would we want to print them? So when we talk about flexible sensors, and whether it's for agriculture or anything else, I think there's some things that we are excited about because it sounds cool, but it may not actually be practical. And I'm a bit of a practical researcher. I try to be, even though I work with nanomaterials. And so here's a little scenario that I pose to many of my grad students that want to work in printing. I have this little RFID band that I got going to a water park with my family. Okay, so it's cheap enough to where they let you take it home with you. They don't make you turn it back in. And yet it is functional enough to where it doesn't allow you to leave with someone else's child. So that's pretty reliable technology. That's pretty cheap. And we've called it a printed RFID for decades. But if you actually pull out the guts of this and look at the tag itself, you would be seeing what you see on the screen here. And I think you can get maybe a pointer. There we go. So you see the tag sitting here. And I often ask my students, how large is the silicon chip with several thousand transistors on it that's the brain behind this printed RFID? And they often like to choose this large looking square, but it's not what it is. It's actually smaller than the tip of this pen. It's a tiny little chip that they've called silicon dust for 2 decades because its cost at scale is fractions of a cent. It has thousands of transistors on it, and it does not inhibit the flexibility of the platform in the slightest. So when you think about whether you want to print something, in this case, the only printed feature is the antenna, metal trace, or if something needs to be flexible, it's really important to determine what the use case will be. Because I think it's pretty easy to argue there's no need for anything else to be flexible in this little wristband. I think there are cases where it is important to have things flexible and in some cases printed in terms of the manufacturer. I list just a short version of what would be a much longer comprehensive list of possibilities and put some pictures over there of perhaps somewhat impractical, but at least visionary ways that you can see the use of printing for these new technologies. So when I talk about printing and the results I want to show today, I want to classify the work that I do in my group as direct write printing. So I give a list on top of some of the features of direct write printing, particularly as it compares to roll-to-roll or template-based printing, where it's more of a high volume approach to go for roll-to-roll, whereas it's more surgical and additional in terms of additive manufacturing for functionality in the direct write space. So specifically, my group works with aerosol jet printing. And in case you're not familiar with printing technologies out there, this is a sort of advancement on inkjet printing, where inkjet would be extruding small micro droplets of a given ink. Aerosol jet first aerosolizes the ink using typically ultrasonic atomization, they call it. And that ink is then pushed through a print line and out of a nozzle with an additional heat flow of inert gas to help minimize clogging. So the advantage of aerosol jet, it has its own challenges as any printing approach would, but it does offer an expansive parametric space for which you can work in. You can use inks over many orders of magnitude of viscosity. And when you're dealing with things like nanomaterials, you may want to tune the ink composition to achieve a certain result. It's great to have that type of range to work from. So when using nanomaterials for that printing space, there are a lot of shared advantages they have in common that you see listed over here on the left. One that is not mentioned in this older review article is the use in solution phase, which I've commented on before. Specifically for nanotubes, which are semiconducting molecules when they are single-walled and they're around 1 nanometer diameter. But they can also be metallic. So some of the early work was focused on isolating individual semiconducting tubes, but that evolved into the use of the nanotubes in arrays, and eventually, not exclusively, but there is a lot of work now in what we would call thin film nanotube-based devices, including those that are printed. And even though you're going to end up with a small percentage of metallic nanotubes present, when you're dealing with microelectronic thin film devices, the averaging effect of the dominant semiconducting presence yields a net semiconducting film. So you can see the overall comparative mobility for these types of films, whether it's a fully printed nanotube device, which is in blue, or just a thin film nanotube device, which may have lithographically patterned electrodes in the gray. The mobility of those films, a key metric for thin film devices, competes incredibly well with some of the leading actually commercial technologies. So polysilicon and metal oxide transistors. In case you haven't been familiar with that space, it's largely driven by displays. So you stare at thin film transistor technology for probably an embarrassing number of hours a day if you look at your phone or you look at a computer screen, because every display out there, unless it's being projected, is being driven by a backplane of thin film transistors, and every pixel being actively controlled by those switches. So this is a dominant part of the electronics industry, the semiconductor industry, that you hear a lot less about when you hear people talk about the needs of regulation. So one of the other advantages to printing nanotubes, I want to compare to printing two-dimensional semiconductors, because we're still riding a bit of a heavy buzz wave on 2D materials, which it makes people want to do anything they can with them. And so, of course, we've printed them. And I hate to break it to those who haven't done this yet, but they are fairly terrible printed semiconductors. Maybe we'll get them to be better, but part of the reason they're terrible is that they do not print into thin films. They print into very thick films on the order of hundreds of nanometers or microns thick, which does not exactly bear fruits from their two-dimensional nature. Nanotubes, on the other hand, actually print into near monolayer films. And that's one of the advantages that can be taken advantage, that can be utilized even when you're in a micron scale thin film device. And you can see an example of a printed film there, 1 to 4 nanometers in thickness. So the few results that I want to talk you through in the next kind of final 10 minutes of my talk, to hopefully leave time for questions, are recent things my group has been doing using the inks from nanotubes and other nanomaterials to develop what we call print-in-place electronics. And so if you think about someone who has no idea what's happening with the forefront of printed electronics, and you just use that phrase, printed electronics, it's likely that what they think in their mind is something like this little cartoon, where someone walks up to a printer, they load a substrate into the electronics printer, they upload an electronic circuit layout that they want, they press print, they wait for some reasonable amount of time, and then they unload fully functional, ready to go electronics. I mean, that makes sense when you think of this phrase printed electronics, right? Unfortunately, even in the foremost of research in the space, it looks something more like this, where you print something and then you move it to the oven, and then you maybe even spin coat something on it, or heaven forbid, go and photolithographically pattern something on it. And at the end of the day, you might even call that a completely printed device. So in the direct write printing world, our lab was really interested in trying to close the gaps here and bring together a printing technique that has all of the functional layers for something as complex as a transistor produced on a single printer. So we started by printing the semi-conducting carbon nanotube layer of a transistor along with the source drain electrodes that are conducting, in this case using silver nanowires, and doing that without removing the substrate from our aerosol jet printer. And you can see the little brief process flow here. We use the substrate as the gate control for the device. And the results actually surprised us. And it made sense when we dug into it further. But you can see in the transistor transfer curves in the middle here that the externally rinsed device, that's the more traditionally processed one where you remove the substrate, rinse off the residual organics outside of the printer, it performed worse than the one that was left in place of the printer. There is a reason for that. It came down to the fact that while the substrate remained on the printer, it remained heated on the platen. So when we performed a rinse to remove the organic residue with the substrate in place, it actually was aided by the thermal energy of the heated platen to drive off a more effective rinse. So we took this to the next step and added in a printed dielectric layer so that the entire transistor was printed. In this case, we loaded Kapton or paper substrate into the printer. We printed the carbon nanotube semiconducting layer first. Then we immediately after that printed the metallic nanowire source drain electrodes. followed by an insulating hexagonal boron nitride layer as the insulator. This ink was developed in collaboration with Tinsei Kasaragi at Manchester. And then finally, we printed a conductive gate electrode. And as the cartoon had shown, immediately removing this, it did not go to the oven or the hot plate. It just went to the probe station, and the transistors were fully functional. In fact, the performance we tested, including their flexibility or operation under strain, which those that were printed on Kapton performed quite well. One of the biggest challenges to this whole approach is to keep these subsequently printed layers from causing intermixing with the former layers. Because all of these are ultimately solution compatible, there has to be a way of keeping those from just meshing together after the print. And so we did that with different additives into the inks and establishing the right type of print sequence. We've also done this with an ion gel as a dielectric. So an advantage of an ion gel is, of course, it drives down the needed voltage for switching the transistor. It's only a 2-volt swing for a full modulation here. The downside is that any ionic dielectric is going to have limitations in terms of switching rate or sweep rate, because you're relying on ionic motion, which is inherently slower. But I don't want to skip ahead here because I want to make sure I cover this last topic to leave some few minutes for questions, is recyclability of the technology. So I mentioned the need to focus more on sustainability for, in this case, thin film transistors for all types of applications. And there are major problems to be dealt with in terms of our overall landscape of electronics. So we took this technique of print-in-place devices that I showed you, and we replaced the insulating layer with a biodegradable printed dielectric. We used a material that's actually very well established in the printed community, including flexible electronics, which is nanocellulose. It's an extract of the fibrils from a plant, and you obtain it through acid hydrolysis. It's almost always used as a substrate, a biodegradable substrate for any other types of electronics. In our case, we developed it into an aqueous ink that is able to yield a dielectric. And it turns out the dielectric is actually an ionic dielectric. There's enough hydration and charge composition to yield a very high functioning electrolytic dielectric film. And that allows for the transistor to operate at really reasonably low voltages. You can see the sequence of the devices here. You load the paper substrate, print the nanotubes, print, in this case, we use graphene as the source drain and the gate electrodes, and then this crystalline nanocellulose as the dielectric. And the resulting devices are not capped or covered in any other way. They're left stored in air and are able to continue to function. In this case, we showed 6 months. We've gone over a year in that data collection at this point. And when you print them onto a paper substrate, you can see the aerosol jet printer running on the left, into transistors, biosensors, capacitors, and whatnot. We then showed that you can reclaim the ink that was printed onto the substrate, the nanotubes and the graphene, separate them into completely recycled inks, and reprint the same devices again. So there's actually a full life cycle that's capable of being achieved in the use of all of the electronic constituents in these devices. So this gives you a bit of a benchmark of the performance of those devices. I won't dig into the small data points, but they looked good compared to other fully printed technologies. And in the most recent month, we published a few papers to sort of advance on a few of these concepts. So first of all, on the printed ionic dielectrics front, because we were one of the first to print these types of dielectrics with aerosol jet, we wanted to examine how they performed with respect to each other, including ion gels and PVDF-based dielectrics. And then another study we did was using printing and other techniques to properly passivate various portions of a transistor-based biosensor. When you have an electronic biosensor that needs to operate in high ionic concentration environments, it's key to have passivation in place that is going to enable a stable type of operation. And so we evaluate that and give some recommendations in this work. A related note here is whenever you're testing devices like this, especially for sensing, it is really important that you have confidence in the stability of the device, that what is changing is related to a target signal of interest. And so we did develop a little custom electronic platform for doing long-term bias stressing of these technologies. And as a bit of a side plug for one of my former PhD students, he kicked off a company selling these little platforms that allow this type of testing to take place. And we've had some really good success on our research results using. So last of the results that I had mentioned in the title that came out just a few months ago is that technique with the all carbon-based inks and recyclability. We adapted it to be a fully aqueous process, meaning that we rely on nothing but water through the print steps. Now, if you've done work with nanomaterial-based inks, particularly carbon nanotubes, you would know this is a significant challenge because nanotubes, while they are able to be effectively dispersed with surfactants in water, they do not print well into high-density films from that particular dispersion. So that was the challenge that we sought to overcome here so that we could use a process that did not rely on hazardous solvents. And you can check out the paper if you're interested in more about that work. So in sort of kind of wrapping this up, there's a lot of other things you can do with aerosol jet printing for different sensing modalities. We do some work with biosensors, including the use of aerosol jet for printing things like antibodies or printing onto bizarre surfaces, including one of my PhD students' fingers. It was a situation of asking for forgiveness rather than permission, but it was not toxic and it did perform just fine, printing conductive traces onto the skin. And he lit a little LED. You could see in his bottom video there that he put on the tip of his finger. So ultimately, this is my last major slide here. There's a lot that can be done with using printed nanomaterial-based electronics in the future. And I think the better we get at being able to explore the possibilities for inks and how to process them, the more of these types of commercial possibilities will present themselves. So conclusion, there's a lot of more work that direct write printing has to offer, I think, for commercial applications, and even the potential for more sustainable electronics. We do a bunch of other things in my lab in case you're interested. You can check out our website there. And I want to make sure to acknowledge the students. They actually do all of the really cool stuff that I just get to talk about, and our many collaborators that have contributed to this work. So happy to answer any questions.